You what?
I'm gonna leave the meeting so that it doesn't like.
Okay, perfect. Sounds good. All righty, recording is started. Mic is on.
And then just share your screen. I'm sharing your screen on Teams.
Yes, you're right. That is a step that I have forgotten a couple times. Screen, let's do entire window. Also share system here.
Okay, guys, we got it. We just started the recording.
Can you see my screen, Fernanda? You should be able to, but I just want to make sure.
Yeah.
Cool. All right. Sweet.
Yes. Thank you.
All right. Do you want me to turn the light? You want me to turn the light?
You guys see better with this?
Is that better?
Yeah, can you come give a speech or something? I'll let you get like, we'll let you get the last one. Yeah, I'll let you get every one.
Okay. I'll do it.
Just done with that.
That's true. Do what?
Most of the engineers, so every.
Oh, okay. Cool. I mean, if you want me to.
I said you should come give a speech at SOAR too.
Every club. My advisor will be like, "What are you doing?" Like, you're just like SideQuest. Yeah, exactly.
Connection.
Do what?
Connection to.
Yeah. Keep going. So, do you want me to go ahead and start?
Yeah.
Okay. All right. So, hello everyone. Hello. Hey. So my name's Devin. I'm gonna get started. For those of you that don't know me, I think I've met probably maybe like half of you, maybe. But I'm Devin. I work for Dr. Vassal. He teaches propulsion this semester, but he taught fluid mechanics last semester. And I'm one of his PhD students. I specifically do CFD, applied CFD type stuff. Right now with Ansys, and maybe I'll kind of dive into some other work as well with other software packages later on. But right now it's all Ansys based, and I do a lot of like multi-phase, like phase transition type of work with that. So I know you're doing more maybe like glider, lift and drag type analysis or wanting to do that. So I've sort of tailored today towards that kind of application. Yeah. So my goal is to take you through a little bit of a simulation that you can hopefully kind of learn how Ansys works, how to set something up, and run a simulation and look at some results. And then with that kind of introduction, then move on and apply it to a glider is my hope for you. So with that, we'll get started. All right, so I'm just doing a little bit of an intro before we get to actually doing some simulation. But Ansys is basically the industry standard in CFD. They have tons of technical support, documentation online, user guide, theory guide, so you can go and like do a deep dive into the software if you're really getting specific with what you want to do. But it's more than just fluids. You can do structural analysis, vibrations. You can do heat transfer, which is part of the fluid package. Or you can do like circuits and that kind of thing, and all sorts of other modeling. But those are some of the big ones that I know of. So good to know that it's powerful in a lot of ways, but we're kind of doing a deep dive into just the fluids side today. So with fluids, you can do things like I just mentioned. You can do lift and drag on, like, let's say a glider or an airfoil, but you can also do things like discrete particle tracking. So maybe you want to look at like how sand will be traversing inside of a wave as the wave breaks on a beach. Or maybe you want to look at something like I look at, where I'm looking at clouds and how clouds will develop. And so I'm looking at, like, let's say soot particles in the atmosphere, and then you have like the thermodynamic conditions and water necessary for cloud formation. You want to study that. So it's got sort of that capability. Or maybe you just want to look at like how snow is like falling through the atmosphere in turbulent wind fields and whatnot. So it's got a variety of, I guess, applications even within fluids that you may or may not think of, because I didn't think of that when I first got into it. So Ansys, for whatever reason, its central software is called Workbench. I think if you search Ansys in Windows, it won't pull up Workbench. Yeah, so I've had that experience where I'm like, why will it not show up? And you have to Google, not Google, but search Workbench. So if you do that, which most of you probably have, but if you go and do that and click on that little image down there, then we'll get started. So, and by the way, I'm sort of treating this free form a little bit. So if anyone has questions, just raise your hand or just interrupt me. And yeah, just let me know if you have any questions. Okay. So the way the Workbench operates is you'll create a project. Looks like this. The way you're going to do that is on the left side of the screen, you'll see a little list of, I guess they call them tools, a toolbox on the left side. You're going to click on this guy. We'll do that together here in a minute, but you're going to find this fluid flow fluent tab, and you're going to drag it over, and it'll create this. So the way that this works is this is like your central hub for the simulation, and it acts, I guess, like a manager is the way I describe it. So it's taking your like almost like a SolidWorks program, your geometry. It takes your meshing software, and it takes your CFD software and kind of pulls it all into one cohesive script, you might say. And then it also has post-processing capability as well. So yeah, that's kind of the way this works. It's going to step through the project with each of those separate software and combine them all in that project. Okay. Okay. So as you can see, I've got two projects up there. That's what I've already done earlier. So we're going to kind of work towards that, but I'm going to do it with you step by step. So what you're going to do is on the left-hand side, find that Fluid Flow Fluent toolbox and click and drag to one of these green squares. And so what that's going to do is create a blank project. So I'll give them maybe a little overview of how this works. If you want to rename it, you can just click down there in the bottom, and I'll rename this maybe test case. And on the right-hand side, these are all the options for whichever software you have selected in that box. So you can see that's changing as I click through these different rows. So like if you click geometry, then it gives you, oh gosh, you can't even read that. Well, I'll read it to you off my screen. But this bar here, analysis type, you can set that to 2D or 3D. That's the only thing I ever change with geometry. Yeah. This is not showing? Okay. I'll also say this, Ansys is a very quirky software. And so I spend about half my day just fighting with it when it does stuff like this. That is a here.
Yeah.
Properties of schematic B2 geometry.
If you go to view,
Yeah.
drop down, there's the properties thing you can check right now.
Yeah. Okay. So you see this view menu here, like Ben was just saying. Click that properties, and did it work?
Yeah.
Cool. Okay. Awesome. Awesome. Yeah. Thank you for letting me know. All right. So if you click that geometry, change the analysis from 3D to 2D, and that's going to simplify the calculations. But if you were doing like a glider, let's say, you could do a three-dimensional geometry as well. So do that for me, and go ahead and give it a save as well, because I try to, whenever I'm doing anything with Ansys, I try to save pretty often in case it crashes unexpectedly. Don't lose everything. And then what you're going to do is right-click on geometry, and you'll see these three different geometry software. These are all distinct geometry generation software in Ansys. I use Design Modeler, but they also have kind of like a SolidWorks one called Space Claim as well, but it's a little bit more of a learning curve. So I just use Design Modeler for simple geometry. So go ahead and give that a click. Okay. Yeah. Yeah. Design model. Yeah. Yeah, don't coach you. Okay. Well, you know. So, if everyone got that, then I'll give you a little bit of a rundown of what you're looking at here. So this is your, geometry window, as you might assume. If you want to come down here in the lower right, you can select what plane you want to be looking at. So select the Z plane, and that'll reorient where you can work on a 2D surface. Then to create a sketch, you just click, you can click this new sketch button here, but what I do is I just click on the plane, and then it sort of auto creates that first sketch. But if you ever want to create a new sketch, there's a button up here to do that. Okay. So then what we're going to do is you got all the geometry options here. So I want to make a rectangle. Let me do this. If you click tools in the upper left, I'm sorry, units, make sure you have meters selected right here. So if you ever need to change your units, you can do that in the upper left. And make sure you have meter there. And then come down here and click rectangle. And go ahead and make a rectangle, kind of like that. So while you're doing that, I'll give you a little bit of background. What we're doing is we're going to have a two-dimensional cylinder, so just a circle in this case, and we're going to run some cross flow over the cylinder. So what this box is an air box. So when you're in doing Ansys simulations, you have to create a fluid domain, and then whatever shape you're wanting to test across is like a negative inside that domain. So we're going to make this be like let's say a box full of air, and then that cylinder is going to be like a circular cutout from that fluid domain. So you can imagine you can make that into an airfoil or of like the glider you're doing, and have that glider cut out instead if you were applying it to that scenario. So if you have that rectangle, then go ahead and click dimensions in this option tree over here, and leave it on general. And then you can click the corner of the box and come down and select the axis and leave a vertical dimension. And you can do the same thing the other half of that box. And then you can click the side length at the bottom to set the horizontal distance of the box. And then I'm going to have a dimension here, so I can sort of position this the way I want. And so as you make those dimensions, you modify them in the tree on the left. They'll all show up right here, and you can just click that and set the dimensions right there. So let's do maybe 30 meters. Yeah, let's do 30 meters wide. And then maybe set that to 15 there to make it even around the y-axis. And then for the other two, set those to 7.5 meters. All right. Then another quirk with Ansys is it doesn't auto-complete things when you're building geometry. So once you set the dimensions and you have your shape there, you click generate to confirm it. And I'll leave that there just for a second so that everyone can do that. Generate, it's this lightning bolt up here, right there. Yeah. So what you'll see here in a minute is we're going to apply a tool to this, and it won't work until you click generate. Okay, so if everyone has that, stop me if you don't. But so this is our air box, like I said. So the next thing we need to do is click, go back to draw in that tree and click on circle and put a circle right in the middle of that air box, and then go back to dimensions and give that a diameter of 1 meter. So, and then click If you notice it's light blue, click generate, and it turns dark blue. So now it's added to this sketch. Okay. So from here, what we're going to do is we're going to take this sketch and we're going to turn it into a continuous surface. So the way you do that is, and this is necessary to make this into something we can actually, I guess what you could say is you're turning it into a part. So you're turning the sketch into like not an extrusion, but you're actually making it into a part per se. So you come here to concept and click on surfaces from sketches. And then this is kind of a quirky thing with Ansys. You're going to open up that XY plane in the tree and select sketch 1. So it's highlighted there in the tree and in your window. And then when you click, you have to click apply under base objects here. And so by selecting sketch 1 and clicking apply, it's now ported sketch 1 into this tool menu down here. Then everything else there, just leave it default. And then click generate. So you'll notice right now it's still just a sketch. This tool is not active until I click generate. And then it turns gray, and that's how you know it worked. Yeah.
Say you wanted to create a surface out of the interior of the circle and leave the rest open. How would you do that? Like, is there a way to like select specifically the interior of the circle to make it a surface?
So,
Or would you even
like,
want to do that?
yeah, I guess it depends on if you would want to.
Yeah.
I mean, there's other tools here, like they have tools where you can create like let's say 2 sketches, and then you can make them both in the surfaces, and then I guess they will be combined, you might say.
Okay.
And so they have a tool where you can, it's called Boolean, where you can like separate them, and you can choose to keep one or the other, or keep both with that Boolean command. So I mean, if you're doing like, let's say an airfoil, then you would kind of do it like this maybe. But if you ran into a scenario where the geometry is more complex, you could build multiple sketches and multiple surfaces, and then use Boolean to sort of cut them apart from each other.
Okay, cool, interesting. Thank
Yeah, yeah. I think Boolean is right. Create, and then there it is. So if you had 2 bodies, you could use Boolean under the create menu. I guess it's grayed out right now because we only have 1, but yeah. Okay, so give it a save. If you haven't saved it, do that. And so now we're pretty much done with this. We're almost done. If you notice down here, this is that surface we just created. That's where that comes from. You can expand it. You can see it's based on sketch 1. And we also have this 1 part, 1 body menu here. So this is that what I said, it's like a part we've made, like, or a body, you might say. And so it has this surface body underneath. Click surface body, and down in the tool menu, you can see like the number of faces, number of edges, number of vertices. You can see your surface area, your thickness, and all that's good just for your own knowledge, statistics and whatnot. But if you go down here to this fluid solid, go ahead and change that to fluid, and that's going to tell Ansys that this is a fluid domain, so that it can propagate that into the next set of tools. And go and give that a save for me. And yeah. we'll go from there. Okay. So tell me if you need me to come back here, and I will. But what you're going to do next, and close out of that quick. There we go. Okay. Let me get out of that real quick. All right. So if we come back to Workbench, we're going to do a lot of this like working in one software, come back to Workbench to control everything and kind of hopping back and forth. So left click on mesh over here on in the little toolbar. You can see that it says the physics is CFD. That's good, all good. Solver is Fluent. That should all be default as far as I'm aware. So we're not going to change anything in this menu. You're just going to right click on mesh and click edit. And this will open up the meshing software. Yeah. Oh, it's gone?
Yeah.
Okay.
This software will. Okay, that's not even on the line. Like it's already over for 30 minutes. You're welcome. I get to be like glasses. Like that should be enough, right?
That's a good note, actually. When we get to like Fluent, there's a similar menu where it'll like make part of your GUI disappear, and you have like a reset configuration button. So remind me, I'll show you where that is here in a second. All right. Were you able to get the meshing opened up? Loading? Okay. I'll wait just a minute because it can be a little bit slow to get open sometimes. Right click on the mesh. Right here. I'll show you. Right click on mesh and then click it. Yeah. Cooking?
Yeah.
We are. Right now we have a. I should have told him. I should have told him. I guess I figured. Well, they might have like a lab or something. I have no idea. Are they just like free?
If applied FBA, I know it's an afternoon class of that, but.
Okay, gotcha. Okay, so if that is opened up, then give you a little rundown of how this works. So similar to Design Modeler, we have this generate button. Feel free to go ahead and give that a click. So what that's going to do is it's just going to give a random mesh to this. I say random, a simplistic mesh to this domain. You won't see it until you actually click mesh in the tree. And then you'll see we've got this super, super coarse, just kind of randomized mesh up there. So meshing can get super complex super quickly. There's tons of tools you can implement, and I know probably like 10% of them, not very many. But you can go down here to statistics, and you can see like how many nodes and how many elements you have currently in this mesh. That's just useful if you just want to kind of double check, like you set some sizing requirements, and you want to make sure it's done everything you want to do. But we're just going to do something not too like complex with this, especially because we want to mesh fairly quickly. So what we're going to do is in this tree, you should see element size right here. Click on default, and then enter in 0.1 for me. And I guess for your knowledge, you might already know this, but if you click that little white box, that'll turn that into a parameter and add it to. So you might have already known that, but all right. So click that, turn it to 0.1, hit generate. Now this might take a minute or two to load in. So we'll be patient with it. So while that's loading, a couple of things you can do with this. Let's see, what's worth mentioning on here? I guess in the bottom right, you have some control of your units. Again, if you need that sort of thing at any point. Oh, there it goes. It's done. Also, you can come over here to the tree and you can view your surface body. I'm not sure there's much worth mentioning at this point, but yeah, all your viewing controls and selection controls are up in this top ribbon. Anytime you want to create a new mesh, you always click generate to make it do what it's going to do. And then you click mesh to view it. So if you ever don't see your mesh there, it's because you haven't clicked on mesh yet in the tree. And then probably a very useful tool is if you're like me and you set the mesh way too small on accident, and it's just sitting here clocking for like 45 minutes. There's a little red square down here as it's meshing. I'll point it out here in a second, but there's that little red square. You can click that to force stop the meshing process. If that ever, I had to do it yesterday because it was just taking forever. So as you can see, it sort of made this pretty regular squared off mesh. Nothing super special about it, but it's a lot finer now, which is, meshing is always this battle between the finer the mesh, the more detail and resolution you get, which is really necessary for certain types of simulations and how accurate you want your results to be. But also the finer it is, you're going to have that calculation time skyrocket. So picking a mesh that's not going to take a week to calculate, but also give you a good resolution to the simulation is a important thing to consider. I think this is pretty good. It meshed in like a minute or two, and at least for what we're doing, I think this is adequate. So the next thing we're going to do is when you have an important feature like this circle we're doing cross flow over, or let's say an airfoil, you might want the mesh really fine next to that object. That way, when you're studying fluid flow over that, you can see a lot of detail around that object. Like I mentioned before, the calculation time versus detail. So we could say, well, let's make the mesh very, very fine directly around the object. And then everywhere else we don't really care, we'll leave it coarser. So another quirk with Ansys, there's these different selection tools up here. There's a smart select now. I think that's a newer feature. But You can use that, or if you want to select an edge, you have to click on edge selecting, and then it'll select that edge. So click the edge of that circle. And then, let's see, right click, click insert or highlight insert, and then click sizing. You can also get there by right clicking on mesh, insert sizing, and then select the circle. If you do it that way, you'll just have to come over here and click apply, like we did in the geometry menu. So either way, this way is a little bit simpler, but then you can come down here and just go ahead and change element size to maybe like instead of 0.1, do 0.01. And leave everything else default, and then just click generate. So here's that red square I was talking about. If you ever need to force stop it, you can click right there. Is yours still clocking? Is it still going? All right, so it finished. Go and click on mesh again, and now you can see that directly on that surface, it's 10 times more fine of a cell size. And so, you know, this is kind of the quick and dirty way of doing it, but you could also implement a lot more controls and have that fineness radiate outwards from the circle. You could fix it from being like these kind of randomly shaped cells to being like, let's say, triangles, or like a tetrahedron, I think is an option. Or you could have it like a uniform curved cell shape and like radiate out from that circle. So there's tons of things you can do, but like I said, I don't know even all of them.
Is there any like documentation on like how to choose iteration?
Yeah. So Ansys has a YouTube channel that has lots of good tutorials, but then also, you know, yes, they do. In the next step, if I don't tell you, remind me. But I plan to talk about it. So yeah. Okay. So if we have that, go ahead. I think we're done with this part. So go ahead and save it for me. And just so you know, you can save from there, or you can save from Workbench. Either way. So was everyone able to get it to load the mesh in? Okay, sweet. Cool. So go back to Workbench. Now this is something unique you have to do. If you want that mesh to import into Fluent for the CFD, you'd actually have to right click on mesh and then click update. And so what that'll do is it'll generate the mesh if you haven't done it yet, and then it'll import it to Fluent. If you have generated the mesh, it'll just import. So go and click on update there. You'll see that it had a lightning bolt right there, and now it's changed to a check mark, so we know we're all good. So now you can left click on setup, and yeah, nothing really to do there. So go ahead and right click setup and click edit. And it'll bring up the launcher. So this launcher, the only things you need to do right now are click double precision, this is going to change the way it handles numbers inside the solver. And double precision will increase your calculation time, but it'll also increase your accuracy, numerical accuracy. So go and click that. This guy, number of solvers, this is how many of your CPU cores you're going to use for the calculation. The more you use, the faster it'll run, but also the more computational power it's going to take. And in the case of laptops do not like this at all. This will run at like 100 Celsius if I run it with more than one core. So I would leave it at 1. But if you have a desktop, I'll run mine with like 20 cores in the lab, so it like really speeds it up. On the student version, they max it at 4. So if you have like a research license, then you can go to like 20 or however. I guess my computer in the lab has 24 cores, so I can go up to 24. But leave that at 1. Other options, I know very little about this, but you can have a GPU also be calculating in parallel with your CPU. If you have a, like an NVIDIA or something like that. You can also set up MPI. MPI is multiple parallel, Michael? Is that what it stands for?
It's a what does it stand for? It's a language for computers to parallelize them.
Yeah, it's
so
like
essentially allows a program to access multiple cores and divide code across them.
that's my understanding is MPI is what like the HPC uses. It has all these nodes, I guess, all of these different computing clusters.
For message passage interface.
Okay.
So like for example, you're running 2 lines. You're running one piece of code across multiple cores. Those codes need to communicate with each other, and you use a message passing interface (MPI) to communicate and essentially keep the code like one piece of code, not 2 pieces of code.
So it allows you to use like lots of clusters, essentially, of computers, and that's what the HPC does. So that's what that is. MPI. I leave it default. I'm not going to use the GPU. I'm just going to use my CPU. And then all of these other, things, I don't have too much experience literally looking at them. So leave it just the one solver process, do double precision and click start. And that'll load up Fluent. And we'll start doing the actual fluid mechanics setup. All right. So when you get that opened up, you'll have this window. This just updates from the most recent thing. You just click OK. Okay, so I'll do a little overview of what you're looking at here. So as you can tell, Ansys is a graphical user interface CFD software. Some like OpenFOAM, what Michael uses are just text-based, so you don't have this, but this is kind of a quality of life type thing. Ansys does have its own like coding language called ADPI. That's what's showing in this window. If you're really good with Ansys, you can run Ansys through ADPI and get very specific with commands and whatnot. But for what I do and what I would say most people I'd recommend is you'll use this as just an informational type thing. It'll kind of output what it's doing to this window for your reference. So over here in this window, you can see your mesh in green. And this is where we'll see like our contours of, let's say, velocity or pressure, whatever you want to view will be in this window. And then on the top ribbon, this is a secondary way to control all your models and tools, but we're going to use the tree on the left. So basically the top is just another way to do the tree on the left. Okay. So starting in the general menu, we're going to look at some of the overarching features that of the fluid mechanics. So for type, we're going to use pressure based. Density based is more for like supersonic flows, compressible flows. And there's certain models like the freezing model, solidification model will not work with density based. So you have to know through the documentation, like I told you about, you have to know what models are compatible with what solvers. So pressure based for low speed flow, that's what we want to use. Velocity formulation, leave it alone. For time, go ahead and click transient. Steady is like calculating one moment in time, or like when there's nothing changing with time. Transient, it'll have that time evolution of the processes. And then for 2D space, leave it on planar. But you could also do like axisymmetric if you had some sort of plane that's rotated around an axis and it's even everywhere. And then if you want gravity, we're not going to do gravity, but if you want gravity, you can check that and set like standard gravity might be y direction negative 9.81. So you have to have the negative in there if you ever did do that. Okay, so transient, pressure based, planar, that's all good. So then on the tree, click the plus icon. It'll open up all of your different models. So like I said, well, I guess I'll just go down through some of these for your reference, but multi-phase is what you'd have if you, let's say, had water and air in the same domain, and you want to see the interaction between water and air or something like that. Energy equation, if you want to see temperature changes, solidification, freezing, melting, anything like that. Okay.
If you have like a substance, it's coming in as a fluid and then goes to a gas, could you also do that just for one substance?
Yeah. I think like you can do evaporation modeling. Yeah, you can do that. So we're going to leave energy off, multi-phase off for what we're doing today. While I'm thinking of it, this little help icon, if you click user guide there, well, as you know, yeah, that'll open up Ansys user guide. You can download that as a PDF, or you can view all of your meshing documentation, how to use the meshing software. They have some general getting started information, or you can go through all of the CFD Fluent information under solution mode. And then if you come up here and search theory guide, so this is the user guide. This is like, here's the tools, how do you implement them? If you search theory guide and then click on, I'm just gonna click on the first one that comes up, and you wanna click the theory guide link. If you do that, then there's a whole separate guide saying, hey, here's a model. This is the theory behind how it works. So like if you want to read up on solidification and modeling, it's like, okay, what is the computer doing to simulate that physical process? And this is how you would read up on that to figure it out. So that's just, useful. If you're like me, Dr. Vassal sends me on go figure out why it's not working trips, and I end up here a lot. So, okay. As a side note, but so go down to your viscous modeling. So this is your turbulence modeling, essentially. It's referred to as, say turbulence or viscous modeling, either way. They have all these different turbulence models. You'll see K omega, K epsilon a lot. Large eddy simulations, you'll see, not that one, but large eddy simulations are another common viscous type model. But we're going to do laminar, keep it simple, keep all the keep the computation time low. We're going to do laminar. So do that, click OK. Radiation, I don't have much experience with. Heat exchanger, species, not a whole lot of experience with those. Discrete phase, if you wanted to, let's say, like I was saying earlier, you want to inject sand into, let's say, a water domain, and you wanted particles that you can accurately track moving through the fluid, you'd use discrete phase modeling. You could use that also for like simulating like maybe like gasoline injection into a cylinder of a car. So that's useful if you ever want to do that. Solidification and melting if you need that. And there's some acoustic structure. Yeah, a few other models. We're just going to deal with just the turbulence modeling for right now. So, okay, do that. Then you have the material plane. So we're going to do air today because that's applicable to your glider. But if you wanted to, let's say, set a new material, if you open up the different menus there, you can see that right now we have air and aluminum. That's just the defaults that you can work with in Ansys or in Fluent. So if you want, like, let's say water, you would do that by double clicking on materials. You have to double click on the materials plane itself. That's kind of a weird thing about Fluent. And then click create and edit. So here you can modify material properties. I guess right now we're modifying that air material, but what we want to do is just get a new one. So Fluent has a whole database of materials, gasoline, water, alcohol, whatnot. So you can click on Fluent database and then scroll all the way down in the menu. And it has this preset water liquid material. You can click that or water vapor, whatever else you want, and then just click copy. And then close that menu. So when you copy it, you can close out of this menu as well because we're not going to modify anything. But now you see we have water liquid in this materials menu. Then let's say you want to modify the properties of water for some reason. I don't know why you, well, I know why you would, but for most applications you might not want to. But you can go to create edit there, and you could change the density of water, viscosity of water, you know, based on what you're doing if you needed to do that. So we're going to kind of stop it right there. Yeah, I'm going to give that a save. Are there any questions based on that? Cool. Okay, so I'm just going to walk my way down through here, a few more steps. So you have cell zone conditions. This is useful if you wanted to, let's say, maybe you're simulating the glider flying at 10,000 meters. So it's going to be very cold in the atmosphere, and you want to represent that cold atmosphere. You can go into cell zone conditions and click on your surface body, edit, and then you can actually modify the temperature of that atmosphere here, or you can change the material of the atmosphere. So you want to say, I want to define that region as water or whatever, you can change it there. We're just going to leave it as air. And yeah, we're going to leave it as air, apply, close out that. And so that takes us to boundary conditions. I'll show you this. So you go back into the cell zone conditions and click fixed values. Oh, well, it's not showing because I don't have the energy equation turned on, but this is where you'd have like a temperature menu here if you had energy equation on, and that's where you could set the temperature if you needed to. Okay, so boundary conditions. Double click boundary conditions, and you'll see, I forgot something. Okay, this is good. This is good. So go back to Workbench. Actually, go back to the meshing software. There's one thing I didn't think to do. Okay, so if you're back in meshing, what we're going to do is we need to name all of these surfaces. That way in Fluent, it'll know we'll have labels for each of these things each of these boundaries we want to modify. We'll have a label for it. So having that edge selector selected, go ahead and select the surface of the circle of the cylinder. It won't always highlight, but in the bottom you can see it says one edge selected. For some reason, it won't always highlight the edges, or it might highlight some and not others. So that's good. You can confirm you selected it. Right click, do create name selection, and then name it something like just cylinder, maybe. Hit enter. And on the left hand side, under mesh, you'll see that edge there selected, or you'll see it's popped up. No, right here. Under name selections, you'll see cylinder pop up there. Yeah, so there's that. So go ahead and click the left-hand face, do a create name selection, name that one inlet. That's where airflow will come in from. Click the right-hand side, create name selection, do outlet. That's where our flow will leave from. And then click the bottom, hold control, and click the top, hold control, click the bottom, and now you'll see it says two edges selected down there. Create name selection and name that walls. Okay. So now you'll see in the left, we have cylinder, inlet, outlet, walls. And then, yeah, once you have that, go back to Workbench, right click on Mesh, and click Update again. And so now it'll have ported those names into Fluent for us. Or it should have at least. Let's see. There we go. So if it doesn't show up, I guess right away, go up there to File and click Refresh Input Data. It'll reload, I guess, from the meshing solver into Fluent. All right, so now we can go ahead and go through our boundary conditions. So whenever you're doing CFD, your boundary conditions are very important. This is where you'll set the velocity of the air coming into your domain. It's where you'll set things as being solid walls, or maybe like a pressure outlet or pressure inlet, where the pressure is causing your fluid flow. So you can set the velocity of the fluid flow or the pressure that's causing the fluid flow, either way. You can set other conditions like symmetry or an axis if you have an axisymmetric flow. But that's really important for here. So we'll start with cylinder. You want that as wall. That's going to make that kind of like a solid entity, you might say. So leave that as wall. If you need to change the properties, you can click edit. And then you can set things like it's a moving wall, or if you had the energy equation turned on, you can set thermal conditions for the wall, like maybe you want a heated wall for some reason. So you do that. For inlet, leave that as velocity inlet. and then click Edit. And under velocity magnitude, change that to 80 meters per second. And you can change the velocity formulation. Just leave it as default, magnitude normal to boundary. But you could change that formulation there if you wanted to. So click Apply. Now we'll be sending our air in at 80 meters per second. Close that. Interior, leave it just as interior. Outlet, leave it as a pressure outlet. I believe it's just going to set that to a 0 gauge pressure. Yeah. So it's just like atmospheric pressure, so that the air can escape out of this domain. So close that, leave it default. And then for walls, just leave it as wall. So a good note is that Fluent will, whenever you name these things in the meshing software, Fluent will recognize certain words and set the boundary condition accordingly, just to make things a little simpler. So because we named that one surface outlet, that's why it chose pressure outlet here, because of the name that you gave it. And then same thing for walls. For cylinder, I guess just assumed that that's probably a wall. Okay, so we're done there. You can close well, don't close boundary conditions, but we'll move on from that. So some of these other things I don't really work with a whole lot. Yeah. Okay, we're going to move on to our solution method here. So there's different solving schemes you can look at under the methods. That gets into the theory guide a lot as far as what will work best for your certain situation. We're going to leave it default for what we're doing for now. Controls can help you with convergence of the simulation if you're having trouble getting it to actually finish or give you good results. You can play with those. We are going to go to monitors. So if you go under monitors, you can set the software to track certain physical quantities. So you can double click on report plots, open up this menu, and then click on new. And what we're going to do is make a lift coefficient and drag coefficient plot. So I'm going to change the name up here to lift. Okay, and then under report definitions, click new, click a force report, and then lift. And under lift, we can select lift coefficient. Change the name. I'm going to set this to lift coefficients definition. And then we want to click print to console and click cylinder under zones. So it's going to calculate it at the cylinder surface. And then click OK. And you'll see this lift coefficient definition appeared under available report definitions. So click that there. I guess it got rid of my name, so we'll do this lift coefficient. And then I think click print to console again, and OK. And so now you'll see that it's been added here to our report plots. So we'll do one more new. We'll do another report definition, do drag instead. Drag coefficient, click cylinder, give it a name. Click print to console, and OK. and you'll see drag's been added to our report definitions. Click drag coefficient, the one you just created. Again, click print to console. And I think that should be good. I gotta give it a name though. Okay. Okay, and you'll see drag coefficient's been added as well. So now, yeah, we should be able to close that now. And I'm gonna give it a save. Was everyone able to get that to set up? Okay. So I think we're almost ready to run this. So the next step is that we've set our boundaries, we set our models. We need to set up the initial conditions of the situation, the simulation. So you double click initialization, and we're just going to let it do its standard initialization of just zero pressure, zero gauge pressure, and then a still environment. But as you add more models and different things to the simulation, it'll pop up like, let's say, temperatures and maybe like turbulence values and different things you can modify or set the initial state here. So click initialize there, and now we've told it what we want the first conditions to be, and then that'll also open up the solution animation window once you do that. So we'll get to that in a second. Double click autosave and change that to 1. Bless you. That'll change that to a 1. What that's going to do is it's going to save the data file after every time step. And then that data file is what you'll use to make your animations later on. So if you want videos of what we're doing, then turn that on to 1 and just click data file quantities. This is where you'll find all of your other, I guess, physical variables that you might want to calculate, but that aren't default in Fluent. So maybe you want to be able to look at density. You can click that and click OK. It just adds it to the list of available quantities to you. All right, so do the autosave, click OK, and then come down here to Solution Animations. Opens up this menu. We're going to create a new object because I figured, well, if you're doing like, let's say, a glider, you might want to look at pressure contours and velocity contours. So click on New and do a contour. Let's give it a name. I'm going to call it pressure. Yeah, I'm just call it pressure object. Object because this is just like the physical quantity setup of what it's monitoring. And then we'll actually set the contour based on this. So then go to contours of pressure here, and then select the type of pressure. I'm going to leave it as static pressure. And then under these surfaces, click in there and do a Control All, so that it's going to display it on all over this. And then click Save Display and close. Then we're going to do that one more time, contours, but instead do velocity. And then velocity magnitude. You could also do components of velocity if you ever needed to, but I'm going to do magnitude. I'm going to name that one velocity object. And again, do all your surfaces and then save display. All right, so now we've made the objects. We're going to actually set the animation. So give that a name. I'll call this one velocity. Click velocity object down there, and then let it record after every 1 time step and set this to in memory. It's just different storage types for the how you want that saved. There are some quirks with this system. as Michael knows, I struggled for days because Fluent does not like anything more than 1080p screens. And so when I was trying to save videos, it kept failing because my monitor was a 2K screen instead of a 1K. And I fought with that for like days trying to get videos saved. So if you have like a 1440p or 4K monitor, just keep that in mind. You might have to force Windows into a 1080p resolution in order to save these videos. Okay, so click velocity object. Okay. And then double click solution animations again to make a new one. Do pressure. Click pressure object. And again, in memory, after every one time step. Okay. And then our solution animations, you'll see pressure and velocity. We've already initialized it. We've set the autosave. So now, double click run calculation. Go ahead and give it a save before we do this. Yeah, I want to go ahead and run this just for time's sake, but yeah, so what we can do is you can have a fixed or an adaptive time step where the computer controls. You can tell it what each time step is going to be every time, or it'll adjust it as it goes based on some criteria you set. You can do the number of time steps. I'm going to say 50 just for not too long of a simulation. Let's do 0.1 as the time step interval, the size. So we'll get 5 seconds of flow time with this setup. This is a pretty coarse time step. A lot of simulations I do are like a millisecond or a microsecond of it's stepping forward each time step. And so I guess for those of you who haven't seen this before, what we're doing is it's going to solve the flow state as like a steady state simulation. And as it's solving, it's calculating each quantity on a cyclical basis, and it's zeroing in on the true value. That like discrepancy between the true value and what it's calculating is called a residual. So as it's doing this cyclical calculating, it's dropping that residual lower and lower. And once that residual hits a certain point, it goes, cool, we're close enough, and it advances a time step and then does the whole thing over again. And so it's this constant process of it like getting more accurate, going, okay, I'm good. It'll jump back up to the next time step. The residuals come down. And so you'll see, in this case, you're not going to see that. I'm not entirely sure why. I think it's because we're not changing a whole lot time step to time step in this. But in most of my simulations, you'll see your residuals do this sawtooth motion of dropping down, saying, okay, I'm good, advancing a time step, doing it all over again. So that's just a good thing to know. And you can set what that limit is. Yeah. Yeah. Mm-hmm. Yeah. And you'll see that here in just a second as it'll be on this little window when I hit go. Okay. So I'm going to do fixed time step. Like I said before, this is the iterations per time step. That's how many times it's zeroing in that residual before it moves on. If it doesn't hit the limit, it'll force it to move on, depending on what that number is. So if you wanted, you could change it to 100, and then it'll be like, it'll sit there and calculate longer before it moves on to the next time step. All right, so I think, yeah, I'm gonna go ahead and calculate. Now we just wait for this should be, I don't know, 2 to 3 minutes, I think is what we'll take to calculate. So in the window here, well, it's all scrunched down. What does that say? So this is velocity. All right, so here you can see the iterations being calculated. These are your residuals printed to the console. And here's your contours. So you can see like we have We can't see it. This is 80. Yellow is 80. So you have your mean flow. You have points where the flow is accelerated on top and bottom. That's your red. And then you have this kind of stagnation point on the front of the cylinder, and you have the blue drag, slower flow behind the cylinder. So, you know, if this was an airfoil, then you'd see your low pressure blizzard velocity. So you'd see the velocity speed up on top right and create that low pressure zone. And on the bottom, you'd see well, I guess it would speed up but less, and then create a higher pressure zone than the top. So yeah, does that answer your question, Fernanda? Cool.
Yes.
Sweet.
Did it need the pressure like at the same time or?
Yeah, so if you click the other window, now it's so little. But yeah, so this is your static pressure. And so you can see the high pressure stagnation point in front, and then even lower. It's symmetric because it's cylinder, right? But you have a low pressure zone on top and bottom, like you can see the airfoil, and then the low pressure in the back. Or I guess higher pressure in the back. I misspoke.
Question.
Yeah.
What do we do if a solution animations doesn't show up?
Oh, initialize it. That's a quirk with it. You have to initialize before that will show up in your. Yeah. So and then it goes down. And then now you can set it to see all the objects. Yeah.
Why mine is stopping up?
It actually went through the whole calculation. Go to animations. That. Play that. Go to switch animations here. Double click prep. Yes, double that pressure one. Click prep. Click. Oh, here. Go ahead there. Sorry. Yeah. Open that up. You can set the pressure. And then edit. Edit off. Okay, close that. Yeah, I was thinking, I mean, when you click, go back to pressure again. Close that again. I mean, I would think that it could be tracking that. It could be something you have to play with a little bit. Like I said, it feels like half of my time spent just fighting it. You know, like why is it not doing what I want to do? Yeah. Yeah. Okay, so
And then now you can do that. You have to work on it. I think it's just telling you the great. It's telling you that that's the code. And then you'll have to go and update it. And then,
I got all the stuff. So sweet. Thank you.
yeah, no problem.
All right. So in the interest of time, I'll go ahead and show you this. So calculation completed. That's all good. So I'm gonna go and give it a save. So now, only thing left to do is do some post-processing. I say post-processing. All I'm gonna do is play the video, but if you wanted to, you can go into Workbench and right-click on results and click edit. And there's a whole software called CFD Post that lets you create nice videos and like slice a 3D object with different planes. If you have like, let's say an engine cylinder and you want to slice through the center of it and see what's happening inside of the cylinder. I'm not going to use it. For what I do, you can do post-processing in Fluent itself. So going to Fluent, this results section down here is basically the same thing as CFD Post, just more rudimentary, less features and things to do, but it's the same concept, same applicability. So you can go down there, open up your animation menu, double click on playback, and then I can select the, see if I can zoom in a little bit on here, maybe. So I can click whichever one I want, let's say velocity, and just go ahead and click play. And then you can see the airflow behind the cylinder oscillating. So that's called a, oh, what is the name for that? Von Karman effect is what that's called. And I forgot to mention this earlier. I based this off of a tutorial on YouTube. So I put the link in the PowerPoint for this. I changed things just to make it more like applicable kind of for this scenario. But if you want to cross-reference that video, he has a really good explanation of some of these concepts as well in there. And it's a little shorter. But I modified it for our purposes here.
This video is where.
I linked it in the PowerPoint. It's in the references of the PowerPoint. Yeah. Cool. Yep. Sounds good. So the PowerPoint's in the Discord is what Fernanda said for, I guess, if you're watching this later. So same thing with pressure. You can hit play on that. You can see how the pressure is evolving, oscillating through those 5 seconds of flow time. Whatever real time you're dealing with is called flow time. That's I guess, I don't know if it's the technical term, but if you're talking about computation time, then that's like the amount of time the computer itself is churning on the problem. Flow time is the physical time that you're simulating. So I know Dr. Vassal has done some simulations where he had the computer, the HPC running for like 2 weeks of computation time. And then for flow time, it was like a second, of real time. So depending on the complexity of your problem, you might have to be patient. So under write record format, let's say we want the velocity video. You go down here, click video file, and then click write. And that'll actually create the video for like a presentation. If you want to do your glider, see the velocity contours come off the air, off the glider airfoil, and then put that into a PowerPoint, let's say. So I'll let that do its thing. This is going to save as an MPEG format, is the file format. For whatever reason, Windows doesn't like MPEG, but PowerPoint does. So well, PowerPoint doesn't like it. It converts it. So I figured out if you try to open the MPEG file, it won't do it. But if you put it into PowerPoint, PowerPoint will auto-convert to an MP4 file. And so if you want to view it, you'll have to do it in PowerPoint. That's my, I'm sure there's other ways, but that's how I've done it. Yeah, exactly. Tricks of the trade. So go into PowerPoint. I will add a slide real quick. And go to Insert. Maybe? Yeah, here we go. Video. This device. So what you're going to do is you're going to find the folder that you created this whole simulation in. For me, I put in this ASME folder. You have a backup folder and a regular folder. You do the regular one. So open that. Then you'll click DP0. And then these are each of those projects. So when I was in Workbench, this is FFF. If you click on geometry, you'll see it says FFF here. If I click on this one, it'll say FFF1. So that's how you know what you're in. So this is FFF2, the one we just did. So go back to your File Explorer in PowerPoint, double-click FFF2, double-click Fluent, and you'll see your video here after you've saved it. So double-click that. You'll see down here it says converting. It's a short video, so sometimes it takes a while, but so you got that. And then we can go ahead and make this one bigger a bit. And you can see your animation. Now, I don't know why, but obviously that's not 5 seconds long. I don't know why it like speeds it up when it does the actual video. There might be a setting you can kind of control that playback speed. But whatever videos you make, you can view them like that. So, yeah, I'll leave it there, I guess. We've got about 19 minutes. So I figured for the rest of the time, whatever specific questions you have, maybe like you haven't gotten into work yet, I can try and help. Or if you just have general questions about how to use Fluent or what it can do, you can go ahead and ask me. So yeah, that's all I want to share. If you have questions, feel free to ask. Yeah.
If I had like a 3D model I wanted to run a simulation on, is there like a quick and easy way of doing that with Ansys, or is that like a whole very small process?
Like the importing of the model, or like you're saying,
like the actual like doing what we just did, of like finding the lift and drag just of like an entire model, like three-dimensional model. Like, how would you go about that, or is that like just really involved trying to do that?
I think it's basically the same process. Okay. But if you noticed when we were setting up those lift and drag coefficients, oh, by the way, lift and drag, that's what we set up. I didn't think about that. So now, of course, I haven't done a whole lot of this, so take that with a little bit of a grain of salt. It's just a circle, so you know it looks a little crazy. But so you'd have to verify this and make sure. I did it for the first time today, lifted, because I don't usually do that. But this is how you could output your contour, your numbers for that. So, and these are your residuals. So it's pretty flat, but this is where I was saying you see that sawtooth design. It'd be in this menu for your residuals. So to answer your question, if you go back to report plots and double click on, let's say, drag or lift, and then click on that lift coefficient definition and edit. How do I edit? Well, I was hoping I could edit it. I'll just create a new one. So I'm gonna go back like we did and do a new lift. And so you see these zones here. My understanding is that you're selecting the zone you want to calculate that force at. So in this case, if you select cylinder, we set cylinder as the name of that boundary in the geometry. So if you had like, let's say a three-dimensional wing of an airplane, you could probably set the bottom surface of the wing as like wing bottom, let's say, and then that would show up here. You click wing bottom, and then it would calculate. Now that'd be three-dimensional, so I'm not exactly sure how that translate, but I think you could just select what you want there.
Gotcha. Okay.
Yeah.
You have to import the wing into the what was it? The first
Design modeler?
geometry.
Yeah.
You have to import it there and then just do the same steps, essentially make a box around it and then make a patch for everything and
Right.
then fit it here, right?
Right. So if you operate in SolidWorks, then there's some sort of plugin for SolidWorks. You might have to play with the settings a little bit from my experience, but you can transfer the SolidWorks model to, I don't think it'd be Design Modeler. Design Modeler is more rudimentary, but if you go back to Workbench, see the space claim here? Space claim is like a SolidWorks, but it's kind of clunky. Takes some time to learn. I've only used it once or twice, but it might put it into space claim. And then from there, yeah, I think the way you do it is you create a three-dimensional box around it as your domain. And then you probably select let's just say the airplane wing and like do like maybe a Boolean and say like delete that and leave a negative of that shape. And then that negative is what it's going to send the flow around.
I see.
You know, I think that's the way it works.
Okay. Very good.
Yeah. I don't have much experience in three-dimensional. Mostly it's
Yeah.
2D and stuff for what I'm doing right now, but yeah.
How does plugin work? So other things directly to SolidWorks, or they have to like drag it somewhere. Is that something extra to SolidWorks?
So you're saying like, how do you transfer from SolidWorks?
Yes, drag it into.
That's a good question. I'm thinking what you do is you probably go into your geometry menu and there's something up here. To be honest, I'm not entirely sure. There's an import thing here where you can import external geometry files. So you might have to go into SolidWorks and save it as a geometry export. And then I think from there, you could probably import the file with this command. And then that would just load it in. That's from, it might be like an STL maybe or something.
I want to run, for example, 10 different and geometry. So you have to save that the file 10 times and then run the same thing 10 times differently. Because
Yeah, like you're saying, the parametrized geometry thing. That's a good question.
Because if I import it directly, the image will need to be redone every time, right? Every time I work on new geometry.
So that's the part I'm not sure about, because that gets into the realm of like a macro file, I think, where you're like changing the SolidWorks, updating it, and then re-saving that geometry file, importing, meshing, and stuff. So there might be like a macro type way to do that, or there could be a way to in SolidWorks, because you can parameterize, is that right? In SolidWorks, and then you might be able to tell SolidWorks export the files maybe every time you do it, and then have Ansys run it. That I'm not too sure about, but yeah, that I'm really not too sure about. But
environment that's not external or external.
I haven't. No. All the stuff I've done is external, like atmospheric type flows. Are you saying like you have like a cylinder and you have like swirling like in the?
It's like, if you have like a thruster, you
Mhm.
can make same cost size.
Yeah, yeah.
I don't want to see the information.
Yeah.
But you can't like.
Yeah.
You can't run like an external. You should have to do anything. Because yes. It's a space within the model that's like.
Yeah.
I was wondering, could you render us to 2D model?
Yeah, you could do that. Yeah. Yeah. It's all about how you set the geometry. I mean, in this case, we set that to a wall and we set that to a wall. So physically, this is kind of like a channel.
Yeah.
So it's sort of like an internal flow, even though we're treating it like an atmosphere. And that's the reason why this is so big, so space. The reason is because we want there to be so much air around it that the effects here are not being influenced by the wall. That's why there's so much space. So like you could, make like a pipes or a cylinder and then have, your air and your gasoline injected and have like a ablation model and a combustion model and particle breakup model and have your discrete particle injection and your, all those kinds of things enabled and have it. And that's where the difficulty comes in of making it all just play nicely together and actually give you results. And then you have to validate the results to make sure they're accurate.
Is there any way to validate the approximation without the window?
To
Validate.
as opposed to like doing like how to calculate drag coefficient.
No, like to validate your results from the CFD.
I mean, you can do like so a good way. So you said a wind tunnel. That's one way. Another way is find a published research paper that has done an experiment and has results. Recreate it yourself, and then, or let's say you're developing a model, implement that model into their scenario, and see if your model gets the same results as they got. So you can kind of base it on a well peer-reviewed previous model, and then use that to see if you get the same results with what you're doing. Yeah, that's one way to. So you can base it off of that other, I guess, simulation baseline. Yeah. Or maybe even just recreate their model and then test it and see if you get the same results.
We kind of got us to out other events.
Okay. Okay. Yeah. That's okay. Fernanda, I guess I'm going to shut down this Teams meeting.
Yeah.
I'm assuming that you'll be able to.
Does the video like stay there? Do you know?
It should go into the chat,
Okay.
and then you can download it from there.
All right.
So let me stop sharing.
Thank you so much.
Yeah.
It was a really good workshop. I've
Good.
done some SolidWorks ones before, and like it's hard to keep people like engaged in doing it. And I was looking at like their computers; they were all like following
Good.
you. It's really nice.
Well, yeah, you're welcome. I'm really glad it was. I hope it was good. I'm glad if it was. So I'll stop doing that, and